Okay, my young Padawans. Feels weird talking to you when you're not here. But hi. What's up? So, I wanted to, since we didn't have enough time in class to go over it specifically, I wanted to go over how to get the symbolic solution for the ball in the cup activity that we've been working on, okay? So just as a review, so we have, here's the golf ball. It's up a certain height from the ground. Let's call it height 1, right? Then it's gonna come and swing down. So now it's right here, and it's a different height off of the ground, right? And it's gonna it's gonna come right there. And when it gets there, we're gonna cut it. You have to make sound effects so the physics is incorrect. Okay. Then you were in charge of telling me where we needed to put the cup. It's a mug, so it's, yeah, that's the cup. You were in charge of telling me where to put it so that the ball would go right in. So let's go ahead and look at the symbolic solution. So first of all, I'm looking at this. D is what I want. D is what I want. So I'm trying to think of all the equations that I know that include D, right? We know work is parallel force times distance. However, after the string is cut, there's not any force acting on the ball in this direction, in the parallel direction. So this isn't gonna help me that much, okay? So that one had D. Let's think of another one that has D. We have velocity is equal to distance over time. Okay, well, time isn't something that we have, but it's something we can use kinematic equations to figure out pretty easily. And velocity isn't something that we have, but there might be another way that we can figure out velocity. So this might actually be kind of useful. So let's just start off really simply by just getting D by itself right now, okay? So it's being divided by T right now. I want to get rid of that, so I'm going to multiply both sides by T. So I'll write it over here. D equals V times T. All right, so now we need to figure out how to get something that can help us figure out what velocity it is right there, and something that can get the time. Let's start with the velocity, though. Let's start with the velocity. So thinking back on our equations that we can use, there are a lot that have velocity in it, that have velocity in them, yeah. But what I notice right off of the bat here is that I have energy up here that's turning into another type of energy. So I'm gonna try and think, okay, what kind of energy is up here? Up here it has gravitational potential energy. And down here, it has kinetic energy and gravitational potential energy, right? Because it's moving now. Up here, before I drop it, it's not moving yet. Then I drop it, it swings down. Now it's moving, but it's still a little ways off the ground, so it still has some gravitational, right? Okay, now I also know that energy can't be created or destroyed in a closed system, right? Well, it can't be created or destroyed, period, but it's gonna be conserved in a closed system, which this is. So what that tells me is that the gravitational potential up here has to equal those, right? Because up here, gravitational is the only kind of energy I have. So the total energy is just gravitational potential. And then this total energy is kinetic and gravitational potential. And since it's conserved, those have to be the same. So what I'm going to say is GP1 is equal to K plus GP2. All right, so how does this help me though? I don't see any V's in that equation. Well, guess what? K equals 1/2 mv squared. And GP equals mgh. Right, so let's just go ahead and plug these in to this equation up here. So GP1 is going to be the mass of the golf ball times G times height 1 is equal to 1/2 mass of the golf ball, velocity squared, plus mass of the golf ball, GH2. All right, now let's simplify this down a little bit. Since every single term has an m in it, I can just divide everything by m and kill it everywhere. Right? Because this is the same thing as writing 1/2 mv squared divided by m plus mgh2 divided by m. So I can cross it out on both of those. So now I'm left with gh1 is equal to 1/2 v squared plus gh2. Now what am I trying to get by itself? Well, this is my final equation that I'm trying to figure out. And v is the thing I need to plug in. So let's get v by itself in here. So first I'm going to get rid of this. I'm going to subtract gh2 from both sides. So we've got gh1 minus gh2 equals 1/2 v squared. All right, now this is in the way, so I'm going to multiply both sides by 2. So I end up with 2gh1 minus oh wait, we got to do it to all of it like that. Yeah, I can't just multiply the 2 to one of these terms. I have to multiply it to that whole side, right? So equals v squared. Now, last thing I got to do is just square root both sides. So we end up with v equals the square root of 2gh1 minus gh2. And I'm going to go ahead and simplify it just one step further because both of these have a g in them. So I'm just going to take that g out so I don't have to type 12 trillion things into my calculator. 2g h1 minus h2. Okay, and this is good for another reason as well. When you simplify it down as far as it can possibly go, you are making it so much more unlikely that you will accidentally make a mistake when you type it into your calculator. If you type it into your calculator 50 times, you're going to make a mistake in one of those times, which not only is bad that you made a mistake, but then if you try and go back to like double check your work, it'll take way too much time and it'll be hard for you to sift through. Anyway, so I would simplify it down as much as you can symbolically, right? Everybody solve symbolically for the love of all that is good. Please. Okay, cool. Sorry. Cool, so now that I've got the V, I can plug it back into my D equals VT equation. So now we've got D equals V, which is square root 2G H1 minus H2 times T. Okay, now the only thing that we have to figure out is T. And for that, we can go to our lovely kinematic equations, right? Now, the key for this one is what's going to eventually stop the golf ball from falling anymore? It's going to hit the floor, right? It's going to hit the floor in the y direction. I want to look at the y direction. Now, take a look at your kinematic equations. We want to find an equation for time. We have a height, so we have a distance in the y direction. Also, in the y direction, there is a force acting, and it's gravity. So it's the acceleration of gravity. Negative 9.8 meters per second squared. So there's lots of good information that I know. I know the y position. I know the acceleration. Also know what speed it starts at. Because in the y direction, when the ball is right here, it's not yet falling, right? So the velocity in the y direction is zero at that point, okay? So initially, right when it starts to fall after we've cut the string, that is 0. So go ahead and try and find a kinematic equation that's gonna work for it. The one that I recommend would be y equals y naught plus v naught t plus 1/2 at squared. Now on your sheet, it doesn't say y, it says x. This is really, really important, so everybody listen. This is important. Even if it says x, all that means is position, okay? So basically what it's telling you is in order to use an equation like this, you have to look at either the x or the y direction. It doesn't mean that it only works in the x direction. It just means you have to pick one. You have to isolate them, okay? So you can absolutely use this equation in the y direction, 100%. Don't have to change a thing. Just remember that it's in the y direction, okay? So I know that my final y is going to be 0 because it's going to land on the ground, right? So 0 equals my initial y is going to be the second height plus, so my initial velocity is 0, so I can just cancel both of those out because 0 times time is 0, plus 1/2 a, which is g, t squared. All right, now I want to get t alone because that's what I need to plug in. So I'm going to subtract h2 over equals 1/2 gt squared, multiply both sides by 2, divide both sides by g, and then we have to take the square root. Now, here's a tricky thing about the signs. So remember, when you're talking about position and forces and all that, the subtraction, like whether it's negative or positive, basically just tells you which direction the thing is going, right? So in this case, so G is pointed down, right? Negative 9.8, it's pointed down. So I'm going to say this is negative G so that those will cancel out. Because if I try and take the square root of a negative, try typing that into your calculator, see what you get. You'll end up with imaginary numbers, which unfortunately are actually a thing, and you do actually use, which is weird, but alas. So anyway, so this was negative, but remember this is also negative, so they can cancel out. So now I'm left with t equals square root of 2h2 over g. All right. So now let's plug that back in up here. So we've got d equals, I don't know if I have enough room. Okay, 2g h1 minus h2 times this thing, which is square root of 2h2 divided by g. All right, now again, remember, I want to simplify this as much as possible. This is ugly and gross, okay? If I have two square roots that are multiplied by each other, I can just put them both under one big square root, right? So I'm going to say big square root 2g h1 minus h2 times 2h2 divided by g. Now, you'll notice my g's actually cancel out. So what does that mean? That means that you could perform this exact same experiment on the moon or on a different planet, and it would not change how far away your cup should be. How cool is that? So cool. Anyway, so my g's canceled out. I have a 2 and a 2, so I'll just multiply them together. So simplified, this is going to be 4h2 from right there times h1 minus h2 square rooted. And that is going to give me my distance that I should put the cup. Do you see how beautiful it is? It's so nice and simple and pretty. Okay, if you had questions about how we did this, write them down and we will go over them, okay? We're gonna have just like a few minutes, not a few minutes, like 15 minutes during class tomorrow to work on this. Yeah. That's it, folks. See you tomorrow. Bye.